All right, let's talk about something that pretty much everyone who works with data in Python has run into. You know that moment when your project just dies? You've hit a wall, a memory error? Well, today we're exploring the tool that lets you smash right through that wall. It's called Dask. Let's get into it. You know the feeling, right? You're deep in the zone. Your data is finally loaded up. You run what you think is a really simple command and poof. Everything just grinds to a halt. You've hit that dreaded wall. We've all been there, just staring at the screen knowing that hours of work might have just gone up in smoke. And the culprit, more often than not, is that infamous memory error. It's such a simple message for such a huge problem, isn't it? All it means is that your dataset is literally too big for your computer's RAM to handle, especially with amazing standard tools like Pandas or NumPy. So what do you do now? And look, this isn't just some minor bug. It's a fundamental scaling problem. The tools we all know and love, Pandas and NumPy, they're fantastic, but they were really designed for data that can fit nice and neatly inside your computer's memory. When your data starts getting bigger, and it always does, you're going to need a new approach. Well, that new approach has a name, Dask. At its heart, it's a parallel computing library. But what makes it so powerful is that it was designed from the ground up to scale the Python tools you already use and love every single day. So why should you choose Dask? Well, yeah, it handles datasets that are way bigger than your memory, which is huge, and it cleverly uses all of your computer's cores to speed things up, which is awesome. But the real genius, the absolute game changer, is its familiar API. This means you don't have to throw away years of experience with Pandas or NumPy. You get to scale up without starting from scratch. Okay, so how on earth does Dask pull this off? How does it let you use pretty much the same code but handle these massive datasets? Well, the secret is this really elegant idea at its core called a task graph. The magic trick here is something called lazy evaluation, and I love this name. Think about it. When you run a normal Python command, it's immediate. You hit enter, the work happens. It's like flipping a light switch. Dask is, well, it's different. It's more like a master architect. It doesn't just start throwing up walls right away. First, it creates a detailed blueprint of the entire job, and the actual construction doesn't start until you give the final go. And this diagram just lays it out perfectly. Over on the left, you've got your Dask collections, your arrays, your data frames. But here's the key. They don't actually hold the data yet. They're just creating that blueprint, which is the task graph you see in the middle. Then, way over on the right, you have the schedulers. That's your construction crew, just waiting for the green light from you to actually start building. Okay, that all sounds great in theory, but what does it actually look like in practice? Let's move to a real example and see how this blueprint analogy plays out with some code. All right, here's some code. We import Dask array as DA, and we create a huge 10,000 by 10,000 array. Then we run a calculation on it. But the most important thing to notice here is the syntax. Does that look familiar? It should. It's exactly the same as NumPy. No new functions to memorize. Now here is where it gets really interesting. When we inspect our result, Y, Dask hasn't actually calculated anything yet. Look at the output. There are no numbers, just a description. All it's done is record the plan, the task graph, and the shape of what the final array will be. Crucially, no significant memory has been used yet. And if we visualize that plan, this is what we get. This is the task graph Dask built under the hood from that one simple line of code. I know it looks complex, but it's just a highly optimized, step-by-step blueprint for getting our final answer. So when does the work actually happen? Right here. It's only when we explicitly call .compute that Dask hands that blueprint over to the scheduler, which executes the plan and finally returns the actual numbers. That, right there, is lazy evaluation in action. So we've seen how it works on a single operation. But what does this all mean for the big picture of your entire data workflow? How does this actually help you scale? The secret to scaling is actually pretty simple. Dask breaks big things into lots of small things. A huge Dask array is just a grid of smaller, manageable NumPy arrays. And, you guessed it, a massive Dask data frame is nothing more than a collection of regular Pandas data frames all stuck together. Dask then runs your computations on all these small chunks at the same time, in parallel. At a higher level, the whole system looks like this. You, the developer, you interact with a client. The client sends those task graphs, the blueprints, to a central scheduler. Think of the scheduler as the project manager. It intelligently distributes all the small tasks to a set of workers, which can be the cores on your laptop or even hundreds of machines in a cluster. So the crucial takeaway is this. Dask separates the planning from the execution. The plan is the task graph. The execution is handled by the scheduler, which breaks that plan into tiny pieces and hands them out to workers. This separation is the key to its incredible power and scalability. By making powerful parallel computing feel just as simple and accessible as writing a line of NumPy or Pandas code, Dask fundamentally changes the scale of problems you can even tackle. So the only question left is, what problems are you going to solve with it?